Hi guys, I hope you are safe and well. So today we will discuss magnetic field, how to compute the magnetic field inside and outside of different conductors with different current distribution. Okay? So we have here an example. A single wire loop is 1.0 centimeter in radius and carries a 650 milliamperes current. Find the magnetic field strength at the center and on the top axis, which is 20 centimeters from the center. So what is the diagram of a single turn wire loop? It would look like this. So this is the diagram of a single turn wire loop. In our example, this will be our radius, the letter A. This is our radius, and this is our center. Ito yung center. The center. And this point is what we call the X. X is the 20 centimeter. Okay, so that should be clear. This line is the radius, the center, and this is the X, the 20 centimeter. Now, we are looking for the magnetic field first, the magnetic field inside, and that is the center, and the magnetic field at point P, which is 20 centimeter away from the center. In physics, we have formulas. So we have different formulas for different current distributions. So we have here for a strong straight line, for a circular loop, this one, and for solenoid, cylindrical, and for solenoid. So we have a formula for the outside. For the center, we have this formula. For inside, we have this formula for a cylindrical conductor. For outside, we have this. For solenoid inside, we have this. For solenoid outside, this is equal to 0. But if you have a straight line, you will just use this formula. In our case, we will be using the circular loop. We have the outside and we have the center or the inside. So we will use the following formula. B is equal to the magnetic permeability constant, current, 2 times the radius, permeability constant, current, square of the radius, 2 times the 20 centimeter, and the radius plus the radius raised to 3 halves. Okay. Now, we first need to know what is the direction of the magnetic field. Imagine this is a circular loop. It's not circle, but yeah, just imagine it's a circular loop. Now, I will use the right-hand rule. We always use the right-hand rule. Now, it might look like I am using my left hand because of the video. It's a mirror image, but in reality, I'm using the right hand. Okay, I'm using the right hand. Now, from the right-hand rule, we will use this. This will be a current, and this one, see this one, the curling one, will be our magnetic field. Now, if your current is going in this direction, so I will hold my wire. So the direction of the magnetic field will be in this direction. It will be curling here, circling this area to here. The magnetic field will be moving like this. Circling. So pag ganun siya, paikot. Pag ganun. That will be the magnetic field. Now, again, we will use the right-hand rule. This is my current. Okay, this is my current. I will curl it. So my magnetic field is curling, circling this way. Again, my current and my magnetic field. Current, magnetic field. So that's why you will have this diagram. And that's why if you do the experiment, you will have this result. As you can see, this is curling, and this is curling. Now, here we will compute what is the magnetic field here and what is the magnetic field here, which is 20 centimeters away from the center. So again, this is our problem. We've identified the formulas. The next thing is to identify the given. We have the following. So be careful, be extra careful. This is constant. We call this the magnetic permeability of a vacuum. This is constant. This is our current. But since we're using milli, please remember to use 10 to the negative 3. This is our radius, which is 1 centimeter. But since we're using centimeter, please remember to use 10 to the negative 2. This is for letter B, 20 centimeter. So please remember to use 10 to the negative 2 for centimeter. And then we will substitute it. So this is our solution. This is our permeability, our current. So since this is milliamperes, we use 10 to the negative 3 amperes. And then our radius, because our radius is in centimeter. So 1 centimeter means to say 1 times 10 to the negative 2 meters. And we will have this answer. To simplify it, we will write it as 40.8 microtesla. So that is the magnetic field in the center of the loop. Now, here we have another one. What is the magnetic field? 20 centimeters away from the center. So this is letter B. So this is the formula. This is constant, the permeability, magnetic permeability of a vacuum constant. This is our I, our A squared, our X, which is 20, our A squared, and then please don't forget to raise the sum of these two to 3 halves. So we have here 3 halves. Then we times it by 2, divide the numerator to the denominator. We will have a long answer, and we can simplify that as 5.08 nanotesla. For cylindrical and solenoid, you can use the inside and the outside formulas, the inside and the outside formulas of different conductors with different current distribution. I hope this short video will help you understand how to compute magnetic field in a single wire loop. And I believe you can also solve for the solenoid and the cylindrical conductors. Thank you so much. Stay safe.